Okay, so I think in the last video I made, I said I'm going to do the string equation next, but I'm not. I'm going to do another heat equation. Okay, so here's what we have. And I'm going to make it a little different and a slightly more general than what I have here in the notes, just to get you some experience doing different things, basically. So we're going to have the t derivative. The t derivative of u is going to be equal to little k. Actually, I'm not going to use k there because I'm going to use k for the eigenfunctions. I'm going to use c times the double x derivative of u. Okay, sorry about that. Okay, and then we're going to have an initial condition, u of x. U of x is 0 is equal to f of x. And then we're going to have different boundary conditions. We're going to assume that the boundaries are insulated. In other words, there's no flux through the boundaries. So I'm thinking about u as being temperature. So there's no flux through the boundaries. In other words, if there's no heat flow through the boundaries, this means that the derivative is going to be equal to 0 there. So we know that the x derivative of u at the left endpoint and the x derivative of u at the right endpoint are both going to be equal to 0. So this is insulated boundaries. And we can mix these up. We could say we have an insulated boundary on one end and it's 0 at another end. So these are called Neumann boundary conditions when you know that the derivatives are equal to 0 at the endpoints. Now you might be wondering what happens if the derivative of f of x is not equal to 0 at the endpoints, or in the previous example, what if f of x is not equal to 0 at the endpoints? And yes, there can be some inconsistencies like that. When we start to look more and more at Fourier series, that will make a little more sense. Okay. All right, so we're going to begin as we do with the method of separation of variables, and we're going to assume that we can write the solution as a product of an h function and an x function. So we're going to look for solutions of the form u of xt is equal to h of t times phi of x. Now, if you want to know, like, whether or not I should write phi of x and h of t, in other words, which variable gets the phi function and which gets the t function, is going to be based on the boundary conditions. So the boundary conditions are at x values. That tells us that it's going to be x that gets us the phi function, and that's what the eigenvalues and eigenvectors are going to be. So if I take this and plug it into the differential equation, I'm going to get the t derivative, h prime of t, over here on the left-hand side is going to be c times h of t times phi double prime of x. We're going to rearrange this in the following way. We're going to have h prime over ch is equal to phi double prime over phi, and this is equal to minus lambda. Okay, we put the c with the h just because it's way easier that way. Okay, so now what this is going to tell us, I'll just record this over here. For now, h of t is going to be equal to some constant, which I will call, instead of calling it c, since I have a c there, I'm going to call it d, e to the minus lambda c t, okay, because of the c there. Okay, and in just a moment, we're going to figure out, that lambda can only be a certain number of values. There's not going to be a solution for every lambda, so let me write this as e to the minus lambda c t. Okay, so now for the phi equation, we're going to have phi double prime is equal, and again, we know, well not again, well sorry, yes again. We know that lambda has to be non-negative because the phi function satisfies the more general boundary conditions. We know phi double prime is equal to minus lambda phi, and we know phi prime of 0 equals phi prime of 1 equals 0. That's that more general set of boundary conditions that we looked at. So the argument from the previous video shows lambda has to be non-negative, but we don't know about 0. And we'll see, in fact, for this case, it can be equal to 0. So phi double prime is equal to minus lambda phi. Okay, again, the previous video shows lambda is non-negative. We now need to figure out what happens if lambda is 0. So, because there are going to be two separate cases, as you'll see. If lambda is equal to 0, this means phi of x is equal to ax plus b. Okay, now our boundary conditions are on phi prime, not on phi. So phi prime of x is equal to a. Now I know phi prime of 0 and phi prime of 1 are both equal to 0, so this says a has to be equal to 0. Otherwise, if I plug in 0 there, it just says phi prime of 0 equals a, so then a has to be 0. Okay, so then phi of x is just equal to b. Does this satisfy the boundary conditions? Well, it does. In this case, phi prime of x is equal to 0. So in this case, lambda equals 0, the constant function is going to be an eigenvalue. So we're good there. Okay. So we'll just have to keep that in our mind, the back of our minds, that 1 is going to be an eigenvalue. That 0 is going to be an eigenvalue, and therefore the function, the constant function 1, or any constant function, is an eigenfunction. Okay, but now if lambda is greater than 0, what are we going to get? And I'll put a lambda here to let us know we're dealing with a specific lambda. So if lambda is greater than 0, we can go through a very similar solution process that we did before. This is going to be a cosine square root of lambda x plus b sine square root of lambda x. Now our boundary conditions are on the derivative, so I need to take a derivative. So phi lambda prime of x is going to be equal to minus square root of lambda, minus square root of lambda a. I can't draw lambdas that don't look like a's. Sometimes I feel like ChatGPT trying to do this. So a, it gets something close, but not quite right. Minus square root of lambda times a sine square root of lambda x, and then plus square root of lambda b cosine square root of lambda x. Okay, so I don't want to keep rewriting this over and over again, but what's going to happen? If you plug in x equals 0, we're going to get 0 here. Well, we're going to get 0 here, so that's 0. And we're going to get 0 here. But cosine of 0 is equal to 1. And so what this tells us then is that b has to be equal to 0. So this term is equal to 0 because sine of 0 is 0. This term is square root of lambda times b times 1. We know lambda is positive because we've already handled the lambda equals 0 case. So this tells us that b has to be equal to 0. Okay. So in other words, this is our solution. A cosine square root of lambda x. Okay. Now if I come down here and look at the boundary condition for 1, so I'm going to remove this. Now I'm going to have 1. Just a sine square root of lambda. Well, this is also equal to 0. And so again, we see that square root of lambda has to be equal to pi 2 pi, so on and so forth. In other words, the square root of lambda has to equal to k pi for k equals 1, 2, 3, 4, so on and so forth. Okay, so then our product solutions over here, for every k, we're going to get a different one. We're going to write this as uk of xt is going to be equal to e to the minus lambda, which is k pi squared, times the little c from up there. Then it's going to be cosine, because b is equal to 0, cosine of of k pi x. And notice that this is going to be for k greater than or equal to 1. This is going to be for k greater than or equal to 1. Now, when k is equal to 0, we have cosine of 0. If k equals 0, that corresponds to lambda being equal to 0. So if k is equal to 0, we have cosine of 0, and we have 1 here, so that kind of works. But we like to say it separately, u0 of x comma t is just going to be equal to 1. This is just going to be equal to 1. And really, for reasons that will make sense in just a moment, I'm going to say that it is actually equal to 1/2. Okay. All right, so this is very similar in structure to what we've done so far, or to what we did in the case where we had the boundary conditions on u were equal to 0. Okay, but just like we saw before, the question that we want to now answer is, in what sense does this satisfy the PDE? Well, it's going to satisfy the PDE, and it's going to satisfy the boundary conditions, but does it satisfy the initial condition? Well, unless f of x just happens to be a multiple of a cosine function, it doesn't. But let's look at a slightly more general situation. What if f of x is not equal to, what if f of x is not equal to one function but a linear combination of cosine functions? So let's say it's of the form a0 times 1/2 plus the sum k equals 1 to n ak cosine of k pi x. Okay, what in this case right here can we say about the solution? Well, in this case we can define u of xt to just be equal to a0 times 1/2 plus the sum k equals 1 to n ak e to the minus k pi squared ct cosine k pi x. Okay, well, does this satisfy everything? Well, yes, it satisfies the PDE, the boundary conditions, and now if you set t equals 0, you get the initial function here. And so this works if we know that f of x can be written as a sum of these cosine functions. Okay, well, let's go one step less, or one step more general. What if we only know that f of x is approximately equal? What if we only know that f of x is approximately equal to this linear combination of the cosine functions? Well, then our solution here is still going to exactly satisfy the PDE, exactly satisfy the boundary conditions, but then is only going to approximately satisfy the initial condition. And maybe that's good enough for us, maybe it isn't. Depends on whatever you're doing. And as I said before, in the coming lectures, we're going to see that actually most functions can be written as an infinite series. We can replace that in with an infinity and replace the approximately equals with the exactly equals, as long as we understand that in the appropriate limiting sense. But for now, we're just going to say f of x can be approximated by this. I'm just going to assert that f of x can be approximated in this fashion right here. And in that case, excuse me, I'm going to assert that f of x can be approximated in this way right here. And in that case, this solution is going to be approximately a solution to this differential equation. An approximate solution to this entire PDE, an exact solution to the PDE and the boundary conditions, an approximate solution to the initial condition. Okay, but the question remains, if you're given an f of x, like x squared or something like that, how do you figure out what these coefficients are? Well, very similar to what we saw before, if you look at the integral from 0 to 1 of 2 times, I'm going to say phi k of x times phi L of x dx. Okay, and over here, let me just define phi k of x is equal to cosine k pi x for k greater than 0, and phi 0 of x is equal to 1/2. This is equal to 0 if k does not equal to L, and it's equal to 1 if k is equal to L. And this is why we want phi 0 to be 1/2. If phi k, phi L, if this is 1/2, well, I made a mistake there. We want it to be 1 over the square root of 2. And the reason we want it to be 1 over the square root of 2, if you have 1 over the square root of 2 times 1 over the square root of 2, it's 1/2, and then this integral is equal to 1. Okay. So then what this tells us, using the very exact same argument that we saw in the previous videos, this tells us in the case that f is literally equal to a finite sum, a linear combination of these cosine functions, then ak is going to be equal to 2 times integral from 0 to 1 f of x phi k of x dx. Okay, and then similar arguments, the exact same arguments that we saw in the previous examples, shows that in the case where f of x is not equal to a linear combination of these cosine functions, then this choice of AKs gives us the best approximation to f in this square integral square thing, or square integral of the square thing. Okay, so what this tells us then is if we know what f of x is, if we have a formula for f of x, we are going to be able to approximate it as a linear combination of cosine functions with these as the coefficients, and then this solution here is going to give us an exact solution to the PDE, an exact solution to the boundary conditions, and an approximate solution to the initial conditions. And just how well that is an approximation, and in what sense it can be made an equality, we are going to be exploring in coming lectures. But just for now, say we're going to take this as good enough for what we need to